From plate tectonics, we're moving on to looking at the properties of seawater itself. And so for that, play properly. There we go. Start with a little bit of chemistry here. Ocean is made up to a large extent of various molecules. Molecule is a chemical combined compound made by two or more atoms. And no surprise for oceanography, the water molecule is the most important one. It's also very, very important in meteorology. What's the formula? What atoms is it made of? Pretty familiar. Good old H2O. We also need to think about how atoms and molecules interact with energy. What we think of as heat is basically how much atoms are vibrating, moving around, energy of motion, kinetic energy. Familiar? Measure using a thermometer. And also pretty familiar with the fact that with changing temperature, we see different things happening with water. If we have solids, the atoms are not vibrating as much, and they are held together in fixed places. If we have liquids, atoms and molecules are vibrating faster, tend to be further apart, and can move around relative to each other. In gases, the individual atoms and molecules have relatively high energy. They are far apart from each other and basically are moving around independent of the others. They'll bounce off of each other, but they're not particularly coordinating with the others. Water is one of very few substances where we often encounter all three of those different states. In solid water, again, the water molecules are arranged into crystals, regular repeating pattern, and bound to each other. In liquid water, the molecules are able to move around relative to each other. When it gets very cold, you start to get some of them lining up. You're kind of starting a little bit on building ice-type structures. And then gas, of course, water vapor. The individual water molecules are moving around independently. Higher the temperature, atoms are moving faster and tend to spread out more. So the hotter the temperature, almost always you have things being less dense. We already saw this in rocks with talk about plate tectonics. Colder, things being more dense. One weird exception is water near its freezing point. Again, ice will float. I've noted this before, but this is because of the open hexagonal shape that the water molecules arrange themselves into in crystals. This is why we have a six-sided pattern of snowflakes. And because of this relatively open arrangement, ice is a little bit less dense than cold water. Liquid, they're moving around more, they can squeeze in somewhat closer. Here's a diagram version of this. Pure water is at its densest just below 4 degrees Celsius, assuming we have ordinary atmospheric pressure. As we get colder, again, we're starting to line the molecules up like making ice, and so that's why it gets denser, so less dense there. Again, this is very unusual. Water does this, but hardly anything else does. Once we get warmer, then around 4 degrees, then it's behaving just like anything else. It's getting less dense as it gets warmer. Likewise, once it has frozen, the ice does get denser as it gets colder, It's just right in this little range here. As we'll see, freshwater numbers are going to be a little bit different for saltwater, but same idea in general. Colder water is going to be denser, but it does funny things right near the freezing point. Water, already mentioned, it's got unusual features, relates to the distinctive structure, and from this it has unusual properties. H2O, if we compare it to similar things, say H2S, if we go down a spot on the periodic table from oxygen to sulfur, or if we go sideways, say HF or H3N or H4C, all those others are gases. Water is liquid at room temperature. Why the difference? Again, it relates to its structure. Melting point and boiling point are quite high compared to most similar compounds. Water also has very high heat capacity. The amount of heat it takes to change the temperature of water, either adding heat to heat it up or the amount of heat you have to take away to cool it off, is quite large. Heard this saying, watched pots never boil. Well, it's not entirely true, but it sure isn't real exciting sitting there watching, waiting for a pot to boil because of the high heat capacity it takes, putting a lot of heat into that water to get it all the way from your starting temperature to actually boil. It also is very good at dissolving lots of things, and these relate to the shape. H2O, it's not a line. Both of the hydrogens are to one side of the oxygen. That's kind of Mickey Mouse look. With this, the oxygen pulls on the electrons more than the hydrogen does. So the electrons with their negative charge spend more time at the O end of our water molecule, leaving less electrons, more positive at the hydrogen end. Negative of oxygen will then be attracted to the positive end of other water molecules. And it's this attraction between the water molecules that leads to all those distinctive properties of the water. For example, being able to dissolve lots of things. If the stuff it's trying to dissolve also has some degree of positive and negative, then the positive and negative ends of the water molecules can associate with those and help things dissolve. For example, we have a crystal of halite, sodium chloride. The sodiums are positive, and that can associate with the negative ends of water and mix in. The chlorines are negative, and so that can associate with the positive ends of water and again be mixed out and dissolved. Now, of course, water is not truly universal solvent. Something that dissolves everything would cause some problems. And there's a joke about the chemist who invented a truly universal solvent. And, well, first of all, couldn't find anything to put it in. Then he spilled some on himself and got absorbed in his work. Seawater, what's it made of? Well, pretty obviously there's some water in there. And also rather familiar salt. Salinity is the measure of how much salt is in water. And most commonly you see it measured in parts per thousand, or PPT. Typically about 35 parts per thousand. Parts per thousand, it's not something we tend to use very often. What would that be, say, percent? Well, percent may not be obvious, but cent means 100, and so percent is same as parts per 100. So 35 parts per thousand is the same as 3.5%. What is the salt? Almost all of it is made up of just 6 different types of ions: sodium, chloride, sulfate, and sulfur and oxygen together, magnesium, calcium, and potassium. Of those, sodium and the chloride are the vast majority, about 86% of the salt in the ocean. Yep, if you evaporate seawater, you get salt. You can pay extra for it at the store and stick it on your food. That's mostly sodium chloride, which is pure sodium chloride is your standard table salt. Well, most table salts iodized to give you a key nutrient there, but sodium chloride is standard salt. Now, some parts of the ocean, like we mentioned for either side of the Isthmus of Panama, are somewhat fresher, somewhat saltier. But it turns out the relative amounts of the sodium, the chloride, the sulfate, the potassium, the calcium, magnesium, those stay very consistent throughout all the oceans. Even if we go back looking through geologic time, say by studying an old salt deposit, we see that they have changed very little over a very long period of time. What this means, again, if you had 2 different samples of seawater, 1 liter of it might give you 37 grams of salt from one place. Another place, you might get only 32 grams of salt from 1 liter of seawater, the rest being water. But if you had more seawater from both places and evaporated enough to get 100 grams of salt from both places, that 100 grams would have the same composition: 55 grams of chloride, 30.6% of sodium, and so forth. So this is referred to as the principle of constant proportion. Although the absolute amount of salt in seawater varies, the total slanty may be a little higher, a little lower, but those relative proportions of the ingredients in the salt stay consistent. This means, for among other things, that if you want to know how salty the ocean is, you can just measure one of the ions. Turns out chloride, well dissociated in bromide and iodide, but there aren't too much of those. That will tell you the slanty. Just measure chloride times 1.8, and you've got your slanty for the ocean. If you're interested in a salt lake, won't work. Different salt lakes have different proportions of things. So this is something true of the ocean, but not of just any salt. Now, there are other ways of measuring slanty as well. These days, there are electronic meters, various other things that you could do. Other things, there are a variety of mineral nutrients, things like nitrogen in the form of stuff like nitrates or ammonia, phosphorus, silicon, iron, various others. Sorts of things you'd see if you were reading the ingredients in a multivitamin. Living things like these, stuff lives in the ocean. So because the living things are using this up, you tend to have relatively low levels of these. There are other chemical reasons as well for some of them. And also, this means that we see different amounts in different places. It's non-conservative. How much of these you find different parts of the ocean, you'd have to go and measure in different places and find out. What else is in the seawater? There are dissolved gases. The most common, nitrogen and oxygen. All those are most common in air, not too surprisingly. There's also appreciable carbon dioxide and noble gases, things like argon, neon, helium, krypton, xenon. Okay, what do these do in the ocean? Well, noble gases, basically nothing. Nitrogen, not much more than that. They are rather inert. They're not doing a whole lot chemically. Now, there's a little bit where nitrogen becomes important. Nitrogen gas, with some types of bacteria or lightning or chemistry labs, it can be turned into more complex nitrogen compounds such as ammonia, nitrogen oxide, so forth. And then once nitrogen is combined with other things, then it becomes an important nutrient. Just plain old nitrogen gas does very little. The other situation where nitrogen does become somewhat important, not exactly in the sea itself, but in things in the sea, is with scuba diving. If you're diving, you're breathing air that is under pressure to balance out the pressure of the seawater pushing down on your lungs. So because the air in your tank and the water is balanced in pressure, you are able to breathe in and out normally. A long tube to the surface, an extra long snorkel does not work. You could breathe out, but not in. And that's not real good for long-term health. So you've got this pressurized air that you're breathing in and out. Under higher pressure, more gas dissolves in liquids. So more nitrogen goes into your blood if you are scuba diving than would be the case if you were at the surface. Now, if you go up and down slowly, as you are taught to do if you're doing scuba diving, no problem. It adjusts back and forth quite readily. But if you come up very fast, then that sudden pressure change can allow some of that nitrogen to come out of solution and become bubbles, similar to what happens when you take the lid off of a bottle of soda, something like that. Bubbles in your bloodstream, that's not something you're supposed to have. In particular, they can block tiny vessels, capillaries. You do not want your bloodstream blocked up. This is bad for you. It doesn't feel good either. It's known as the bins. It can be treated, but it's bad for your health. And once you've done that, then pretty much your scuba diving is over. So you do get that issue, but other than that, nitrogen noble gases aren't really doing much. The name noble gas refers to the nobles as I am noble. You are a commoner. Not mixing. So in the ocean, yeah, there's dissolved nitrogen, yeah, there's dissolved noble gases, but they're doing very little. Oxygen and carbon dioxide, on the other hand, living things are interacting with those. They are much more chemically reactive, so we're going to see things changing much more with oxygen and carbon dioxide than those others. There are also a variety of trace elements. You can find practically the whole periodic table, as long as you don't get into the stuff that's only been made in labs, in the ocean. Not much of a lot of them, but they're there. This may be all the way parts per million or even parts per billion. So for example, yes, there is gold dissolved in seawater. And it's a classic scam to have a company that is supposed to be extracting the gold from seawater. The total amount of gold in the whole ocean sounds pretty impressive, but how much work it is to try to get that out and get enough of it to be worth anything, nah, that's not going to be real practical. Even something that does occur in rather small amounts can be quite important to living things, either positively or negatively, for that matter. There are a number of elements where you need a little bit, but too much is poisonous. selenium, iron, a lot of things there. There are also a variety of more complex organic molecules. And organic mean carbon-based, like typical molecules that we associate with living things. Fats, carbs, proteins, various hormones, vitamins, stuff like that. There are small amounts in the ocean. These may be released as living things die and decay, or they may be produced and more deliberately released by living things. For example, if you've ever picked up ocean, or for that matter, freshwater creatures, you notice a lot of them are kind of slimy. That slime covering provides some thing of a smooth surface, so easier to move through the water. Often there's some antibiotics and there's some other advantages as well. But that's also going to be coming out into the water. The animal has to keep producing more slime as it loses some. And then those molecules are floating around in the water, and other things may absorb them as a food source, things of that sort. Looking a little bit more at the pattern of salts in the ocean. Again, average salinity, the amounts of particularly the major components, is quite consistent. It's not changing. Steady state, what this means is, yes, there is salt coming in, there is salt going out, but those two are in a balance, and so the total amount in the oceans is staying quite constant. Salt going in now, where does it come from? Where is it going? Well, part of it comes from the weathering and erosion of rocks up on land. Weathering is specifically the process of rock breaking down into smaller pieces as it is exposed at the surface. This includes both physical and chemical processes. Erosion is then the transport of these pieces, carrying them away. And these lead to a variety of minerals being available to dissolve in water and end up as salt in the oceans. We also have chemical reactions of especially hot rock and lava with seawater that allows salt to come into the ocean. I mentioned that a little bit earlier. Rainwater is naturally a little acidic. When carbon dioxide dissolves in water, it makes it a little bit acidic, and that helps it chemically attack the rocks. And of course, as pieces break, that's much easier for the pieces to then be exposed to air and water and have more chemical things happen. And as they change chemically, that tends to break down the previously existing connections between the pieces. So the two processes work together, physical and chemical weathering. Here's an example of the deep sea. This structure is known as a black smoker. Not too hard to figure out why. That smoke is actually tiny bits of minerals and bacteria that are getting energy from the minerals coming from very hot water down in the sea floor, emerging out at this spot along mid-ocean ridges. How hot is it? Well, one of the first submersible trips down, observing these. Okay, let's check how hot it is. So they got a thermometer into the robot arm of the submersible and stuck it into the water coming out of the black smoker, and the thermometer melted. That's hot. Turned out with somewhat sturdier thermometers that the water may be as much as 400 Celsius. That's rather more than your oven. So that extreme temperature, there's lots of chemical action going on. Why isn't it steam? Because it's under a huge amount of water, and all that pressure keeps it from actually boiling, but extremely hot. Lots of chemical reaction, dissolves stuff out, carries it into the ocean, hits the colder seawater. Some of those minerals are precipitating out, so that's part of the smoke-looking stuff. And then again, there's lots of bacteria getting energy from those minerals, and there are things eating the bacteria on up the food chain. How about losing salt? How can we have salt come out of the ocean? Well, one example of it might be familiar if you've ever dealt with stuff that's been around the ocean for an extended period of time, illustrated by the issue of if you were to get a used car, would you rather get one that had been kept near the beach or, say, in Boiling Springs, assuming that similar age, similar miles, been cared for similarly? In that case, you'd better choose the one from around Boiling Springs, because the one from near the ocean is likely to be somewhat rustier. We have salt that gets into the air. As the wind blows, you get tiny drops of salt water, and as the water evaporates, that leaves tiny specks of salt blowing in the air, and these can blow onto land. The salt will affect whether there's any metal that can rust due to the chemical effects of the salt. It can kill plants that don't tolerate salt. It contributes to the smell of being near the ocean, things like that. There's also chemical interaction with the bottom of the ocean, whether it's the clay minerals down there, cooler conditions. There are minerals that can actually precipitate out of water and take the dissolved stuff out that way. Living things building their skeletons. Again, some of those chemical reactions don't just bring stuff into the ocean, but can also take things out. Evaporation. Evaporation itself does not actually take salt away. It's the water that evaporates, not the salt. But it is true, if we have enough water that evaporates, the very salty water that's left, that may be so salty that we start to have crystals precipitating out. And so that could lead to some salt being removed from the ocean. For example, we have salt water getting up on the beach into a crack, and then that water evaporates, leaves salt behind, that sort of thing. That is taking salt out, but it's not exactly the evaporation that's doing that. It's the precipitation of the salt, which then results from evaporation. Looking at different things in the seawater, we can look at their residence time. What this is the balance between how much is coming in and how long it stays in the ocean. An average length of time that a particular ion, say one sodium ion, is floating around in the ocean before it ends up somewhere else. Anything with a rather long residence time, that means it spends a lot of time in the ocean. So those will tend to build up in the ocean. If it's got a short residence time, that's something that when it's in the ocean, pretty soon it's out again. Whether it ends up sinking down to the bottom, perhaps, or used up by living things, whatever it is, it doesn't stay there long. Turns out to mix ocean water all the way around the globe takes about 300 years at present. So if something has a rather long residence time, much more than 300 years, then it's going to get mixed all the way around the ocean, and anywhere in the ocean has about the same amount of it. That explains our law of constant proportions. Things that have a long residence time are going to have constant proportions. They're mixed throughout the oceans. anything that tends to stay in the ocean less than a few hundred years before it can be mixed all the way around and evened out, it's already going back out again. So short residence time, not consistent proportions. A different example of residence time that may help you picture it is how long do folks tend to stay at a college? Well, it depends. Students tend to have a shorter residence time, typically 4 years. Some folks may go through a bit quicker, some longer, maybe do graduate school or the like. But typical residence time for a student at college would be 4 years. Professors, on the other hand, we tend to be stuck here a lot longer. Whether we're wanting to do something else, well, we're here, so evidently we like it here, but we're resident for a much longer period of time, typically, than students. So we, correspondingly, if you look at the directory of students, that changes a lot faster. The directory of faculty changes slower. Same idea, different types of things in the ocean tend to be there for shorter or longer periods of time. Seawater is salty. That means it doesn't behave exactly like pure freshwater does. For example, pure freshwater will freeze at 0 degrees Celsius. If we add salt to water, what does that do to the freezing point? Well, you're probably familiar with some examples of adding salt, whether it's dumping salt on roads and sidewalks and the like in winter, or if you've ever done the old-fashioned sit there and turn the crank, ice cream churning. Characteristically, salt is mixed with ice, packed around in the freezer compartment, because having the salt lowers the freezing point. It has to be colder to freeze salt water than fresh. Basically, salt is not water. So those salt ions don't fit into that nice hexagonal structure of the water crystals, and they're getting in the way, makes it harder for the water to get all lined up and build the crystal. Adding salt. Now, if you take a bit of salt and drop in water, some of it dissolves, but the rest sinks. Salt is denser than water. So when we mix salt with water, it's going to be denser than pure water. We also have somewhat less evaporation and a higher boiling point because salt gets in the way of water molecules escaping. Again, salt does not evaporate, well, not at any earth temperature you get outside of a volcano anyway. And so it's only the water molecules can evaporate. If we've got other molecules besides water around, that's going to decrease the evaporation. So boiling temperature of seawater is higher, and freezing point is lower. Good point to pause here, and then we'll take up more features of seawater.